Resident Evil 4, a really fun remake of the original. Welcome to CS302 Assignment 8. And for the assignment, we're going to again sort of revisit Resident Evil 4. And of course, the main theme of Resident Evil 4 is, of course, to save Ashley. And of course, originally in the game, you have to locate Ashley at the church. And of course, throughout the game, Ashley either sort of goes into a trance, and also at times she gets sort of captured. So of course, Leon's job is always save Ashley. So in this, I guess, program, we're going to have it where the game originally starts, where Leon starts in the village, and then Leon has to battle through the zombies. Although I don't think they're called zombies in Resident Evil 4, but in reality, they really are just zombies of Resident Evil 4. And you have to, battle through different areas of the map to reach Ashley. So for this program, what's going to happen is we're going to have a graph where we have several nodes which have different locations. And of course, our edges will connect a path between any two locations. Each location has a set of these zombies, and then Leon has a set of ammo. So it takes one ammo per zombie. So if you play Resident Evil 2, you don't ever defeat the zombies. You typically fire to their head to daze the zombie and then run past them. So in this example, that's what Leon will do. So if Leon is at a node that has 5 zombies, he needs 5 pieces of ammo to be able to get past that location onto other locations. So here is the actual, this first paragraph is just the introduction of the story, but it's going to be the list of the locations. It's going to be your node names, essentially. So you'd have to do some kind of a DFS traversal. However, you may have to revisit nodes more than one time if a better path was found. So before I go into the more technicalities of the program, if you ever play Resident Evil 2, 3, or 4, any of the Resident Evil games, sometimes on the more difficult sort of gameplay, what you do is you save at a certain spot. You do like a pilot run. You try to attack or try to fight a certain part of the game. You realize how you didn't really play that wisely, so you go back to the previous save and then try again. So in this DFS traversal, consider every DFS function call as a save point. And you go back to previous save points and try other paths, and maybe a different path, you play it wisely and then get to Ashley in the different path. So of course, that one, I'll sort of discuss that more later on in this video. That's essentially going to be the preliminaries of this program. So now let's go ahead and talk about the actual data structures needed to implement this modified DFS traversal. So the first data structure is going to be your adjacency list. And you can see here, we're using a map because, well, each node is going to be labeled by a string. So we're going to think of the string as really sort of an index of the node, if you will. So for the examples in class, I always use index 0 through v-1 because we label our nodes with integers or indices. So here we're going to be using a string as our node name. So we're going to map sort of a location name to a list of, or a linked list of strings, which these are going to be a linked list of all the neighbors of this node right here. And I call the adjacency list, but of course, feel free to give it any creative name as you would like, but you want to have this map. So a string that maps to a linked list of strings. Notice list is a member of STL, which means you don't have to create your own custom linked list. This list class implements a doubly linked list for you. So again, this assignment is really designed to help you see how linked lists aren't really that bad. It's just implementation is not fun, but the whole concept is really cool how linked lists works. So there we are. So of course, you're going to populate this sort of structure sort of edge by edge. But again, I'll go over the input portion, which will show you how you would do this. The next data structure is going to be, well, enemies at a location. So you want to know how many zombies there are at any particular location in your graph. So it's going to be a map that maps a location name to an integer that tells you how many enemies there are at that location. So that's sort of self-explanatory. Now, this right here, this is going to be really your visited or your quote-unquote visited array, because you want to mark, so whenever you land at a location, you want to store how much ammo you had when you arrived at the location, especially if you have more ammo right now. So initially, this map, everything will contain 0 by default. When you first arrive at a location, if your ammo amount is bigger than 0, which it will be, you overwrite the amount of ammo you have at this location. And as you traverse the graph, if you do end up coming back to the same node, but in a different path, you end up having more ammo than previously stored in this location, you update this map at this location and you revisit the node. So again, I'll do a nice traversal so you can kind of get an idea of that. But this is going to be really your visited array. You may revisit a node more than once, but the thing is that you want to make sure you only revisit a node if the amount of ammo you have is more than the last time you were at this location, or the largest amount of ammo you had at any given time before you arrived right now. I think I might have just overdid that a little bit, but anyway, I'll show you what this kind of how you want to think about this. Then the last structure here is going to be your predecessor array. This is going to be needed if you want to, of course, output the path Leon took from the village to the church, that path that Leon took to find Ashley. So that's going to be your data structures needed. So to input in this program, you'll be given two sort of files. You have to, of course, open a file stream to read it. Your first file is going to contain a set of lines. Each line contains a location, a from location space to location, that tells you the details of an edge. So for example, if you have, let's say, on a line, village space lake, that means there is an edge from village to lake. So of course you would read in, your from and to locations, and this is going to insert this into a dependency list. So from, there is an edge from to. And of course you have to, constantly read a line, use the from to look up a particular linked list, and then push this back to that linked list. So you're essentially inserting all of your neighbors of from. So that's all you have to do, really. Now, of course, if you want to traverse your sort of list, so consider we're at some locations. Let's say location is a string. Let's say it contains, let me see, I think ballroom is one of the locations in Resident Evil 4. So consider that location is a string that contains ballroom. This for loop will iterate through all the neighbors of ballroom. So you can create this auto type, which is going to be an iterator. You assign it to the begin, and while it's not equal to the end, you update it by moving it to the right by 1. And then star neighbor is going to dereference this iterator. It's going to retrieve the string or that node name of one of location's neighbors. And here's an alternative way, which I actually chose this way because it's actually way more concise. When you look at how much more nifty it is. You have for auto neighbor. This is going to iterate each neighbor of location, but now neighbor is going to be a string, not a linked list iterator. So neighbor is, you can literally just use the word neighbor. That's going to give you the neighbor name of location. So let's say if location is ballroom, you have neighbors lake, cargo depot, and mines. The neighbor is going to be a string that contains cargo depot, mines, and I forgot the other one, but you get the idea. So those are two ways you can iterate through all the neighbors. And of course, this one you have to dereference, but here this is a range-based loop. So neighbor will be a string type. This is a regular for loop, and you have an iterator. That's a linked list string iterator. That's the difference between these two. So I don't want to over explain that and get myself confused right here. So of course you would use this in your DFS traversal to traverse each neighbor and call DFS function on each neighbor of a location. And of course your other file you're going to be given is going to be just a file that contains essentially the enemies at each location. So each line of this file contains a location name, space, integer. And you're going to store the amount into that enemies at location map. So you want to have a separate map that just tells you how many enemies you have at any particular location. Very simple. You can use a bracket operator, or you can use insert function, whatever you want to do to just insert the location name has to map to an amount. So that's going to be just the basic data structures. So let's now go over the main algorithm. I'll first give you the function prototype, and then of course I'll do a simple, kind of a quick demonstration of how you want to think about the DFS type traversal for this program. Okay, so this is going to be the Boolean function, your DFS function. Of course, it has to be a Boolean. And of course, you can call it anything you want to call it, but I called it save actually because, well, that's the point of the program and the point of Resident Evil 4, so why not? So let's go over all the parameters you're passing into this function. So of course, this string Leon, that's like your current. So whenever I went over DFS in class, that's going to be your current. So basically it tells you which the node name that Leon is currently on. This parameter is the amount of ammo Leon has when Leon lands on this particular node that Leon's currently on. Then of course I called it map. That's going to be your JSON-C list. Your enemies at location. So it maps the name to the amount of enemies you have. Then you have the visit hit array, or called the ammo at location. This is a reference parameter because this might get updated in each function. So you want to have the update take place in future functions as well. So of course, it's going to be passed by a reference. And of course, you have your predecessor array, which you update accordingly. So as you traverse to a new node, you update predecessors similarly to the regular DFS traversal. And again, it's going to be a reference parameter because you can update this. So of course, remember, you're going to be sort of a map string to a string. So it's going to be, this is going to be the predecessor of that key. So the value is the predecessor of the key. Just same ideas in class, except instead of using integers, we're using strings. So an unordered map really can be thought of as just an array where the indices aren't going to be integers, but they're going to be other types, such as a string. So anyway, that's the idea. So of course, the way this function works is you return true once Leon equals the church. Oops, I think I misspelled. It's supposed to be Leon, not lean, but that's okay. So, you know, I'll fix that before I upload this. So Leon equals church. When that happens, that means Leon found the way to the church. So true, he saved Ashley. Then otherwise, if it's not the church, of course, then you have to run that DFS traversal. You have to make sure that when you arrive at this node, the amount of ammo you have is more than the amount of ammo you had the last time you were at the location using this ammo location map. And of course, you have to, you know, call this save Ashley function on every possible neighbor. If one of those neighbors returns true, that means a path was found, so return true, relay all the way back to the beginning. If let's say you call this DFS function on a neighbor returns false, then you have to, of course, try the other neighbor and continue. And of course, you return false at the very end if every single path from Leon's current spot all leads to a failure. Then return false back to the previous save point, and from a previous save point, it will try a different approach. So all you're doing is, and every time you go to a new node, imagine you first save your progress, and we return back, you return back to previous save points, then you try a different path. Maybe this other path will lead to will lead to a success. So anyway, let me go ahead and give you a visualization of the first, or I guess of the other, I guess not other, but of the input files and the actual graphs you're going to be dealing with in the assignment. Okay, so this is going to be the picture of the map 1 and enemies 1. So the numbers right there On top of each node name is the enemies at each location. And I drew out this where the red arrows denote the actual path that leads to the village to the church, or so Leon's able to reach Ashley and save Ashley. Now, the input is designed, or at least from the best of my ability, I designed it carefully where there's only one possible solution. So there's many different paths you can take, but there should be only one solution. And every input will work where there will be a solution, there will be a path that saves Ashley. I mean, I did not have the heart to create an input case where Ashley does not get saved. In fact, whenever I play Resident Evil 4 and one of those zombies captures Ashley, walks away with her, and if I'm not able to save her in time, I lose the game, I get really mad because I feel like I failed Ashley. So of course, we're going to make sure that we don't, there's no input case in this program where Ashley won't be saved. And every input has a solution. Now, of course, another thing you have to check for is don't just modify the order of the input. So as you're reading an input from the file into your adjacency list, don't modify the order, because of course what you could do is you could make it where the neighbors of village, oh, it happens to have Grand Hall be the first neighbor, and then of course Grand Hall's first neighbor could be Mines, and so forth. So, well, of course, Grand only has one neighbor, but Mines, of course, I'm going to make it where you're going to have to sort of do some backtracking, because, of course, that makes the program more interesting. So don't actually format your, or rearrange your neighbors list in such a way where you just have one pass through and solve it. Make sure you have to go back. So I have the input set up in a way where you're going to have to backtrack at least once to make your program a little bit more interesting. So of course, if you do try to rearrange it, we will take off a hefty amount of points, because that implies that you weren't, if you're doing that, that means you probably weren't able to write this recursive backtracking algorithm. So anyway, so the village always will have 0 enemies, because as you know, when you play your second playthrough of Resident Evil 4, you know that in the village scene, you can run to the roof of one of the buildings and you can shoot, I believe, the church bells, and then all the enemies decide to just sort of stop harassing Leon. So I guess for that reason, there'll be always no enemies at the village. I mean, why would you not apply that trick in multiple playthroughs than going through that entire process every single time? So initially, your first function call, you of course in main you would pass in village as your Leon starting point. So the Leon parameter would contain village initially, and the ammo is going to be 10 initially. So what's going to happen is, as you look through all the neighbors, suppose the first neighbor you're going to look at in village will be castle. So you see that castle has 7 enemies, so you have 10 ammo, which means you're able to actually go to the castle. So your second function call, you would jump to castle, and you would have 3 ammos. So you actually would store the value 3. So we have that map, the ammo at location map. For castle, store 3, which means 3 is the max amount of ammo you had so far in the castle. Then from castle, suppose your next neighbor you take is, let's say you happen to go to Grand Hall next. So of course, from Grand Hall, you actually have 3 ammo at castle. There's 2 enemies at Grand Hall, so you can go to this location. So your third function call would be Grand Hall with 1 ammo, because you had 3 ammo here, but you had to take out these 2 enemies at this location, so it took up 2 ammos, so you have 1 at Grand Hall. From Grand Hall, you go to, of course, you go to Mines. You have nowhere else you can go. And for Mines, well, you actually, your fourth function call, you would have actually 0 ammo here, because you technically can make the trip to this one, or you can treat this as if you have 0 at any point, you can sort of backtrack. But for now, we'll just go to this node with 0 ammo. Then from Mines, we can't go to clock tower or island because in both cases there are at least one enemy in both spots. You have 0 ammo, so you're not able to go to clock tower or island. So from mines, you have to return false back to Grand Hall. So consider that these functioning calls that are like, so functioning call 1, 2, and 3 are all save points. So at function call 4, you didn't really play the game smart, so you're going to go back and just sort of load your previous save point, go back to the previous spot, the Grand Hall, and try a different path. So from Grand Hall, there's nowhere else you can go. You tried its only neighbor, so you go back to Castle. You return false back to Castle, or you reload a previous save point. So you go back to Castle, and you, of course, you remember you had 3 ammo when you were at Castle before you went to Grand Hall. So you try to Grand Hall, return a false, which means, okay, let's try a different neighbor for Castle. So next neighbor would be Mines. You've already been to Mines, but the last time you were at Mines, you had 0 ammo. This time you would have 2, because you have 3 ammo, minus the 1 enemy at the Mines, you would have actually 2 ammo. So for your 5th function call, you jump back to Mines, and you overwrite this amount to be 2, because now you have 2 ammo, which you didn't have before. You have more than you had before, so maybe having more this time around, maybe it's going to lead to a better success. So from Mines, I guess you would try Clock Tower. I guess why not try Clock Tower next? From Clock Tower, you go to that node, and you see they have 1 enemy, so your 6th function call, you use up 1 ammo to take out that 1 enemy, so you have 1 at this 1 bullet at this location. So from Clock Tower, you can't go to Ballroom or to Cargo Depot because both cases there's more enemies than you have ammo, so you would not even try either neighbor, so you return a false back to the previous function. So you go back to Mines, and you remember at Mines, you remember that you had 2 bullets at that location. So you tried Clock Tower, now let's try Island. Well, you can't go to Island because you have 5 enemies, you have 2 ammo, can't be done. So you have to go back to a previous save point or reload the game. So you load the game back to Castle. From Castle, well, you tried Grand Hall and Mines. Both functioning calls return a false back to you. So you return a false back to Village. So you reload the very beginning of the game where you had 10 ammo at Village. So now you know that you already tried going to the castle. That was not a good idea. So how about this time we try to go to Grand Hall? So, okay, so now if you go to Grand Hall, you notice that, oh, well, I have 10 ammo at Village since I loaded the game from the very beginning. I have 2 enemies at Grand Hall, so for my 7th function call, I'm going to go back to Grand Hall, but this time I'm going to have 8 ammo, which means that even though I've been to Grand Hall before, but I found a new path to Grand Hall that has more ammo this time, so maybe having 8, ammo instead of 1 might actually lead to a success. So now we look at Grand Hall's neighbor. So you have 1 neighbor, Mines. And the last time we were at Mines, we had 2 sort of ammo at that location. But now if you go to Mines this time around, we would actually have 7, because we have 8 at Grand Hall and -1 because you have 1 enemy at the Mines. So our 8th function call, you would update this amount to be 7. So now our max amount of ammo we had at Mines is with 7 this time around. So of course, we can go through the motions, but I'll just shortcut this. But of course, we can now try, if you try Island, we of course return back a false because we weren't going to be able to make it there. But we'll just shorten this video a little bit right now. I'll just say that. Let's just try Mines next. And then this will be our 9th function call. And of course, this time around, we would have actually 6 ammunition because we had 7 at Mines and we had 1 enemy at Clock Tower. So of course, we go there. Let's suppose from Clock Tower, we just go to Ballroom. So I'm going to shorten this a little bit. So we go to Ballroom for our 10th function call. And of course, you would have 4 ammo over here. And of course, from Ballroom, we have 1 neighbor, Church. And we can go to Church because we have 2 enemies. You have 4 ammo. So of course, you go to Church. And we would have actually 2 ammunition when we arrive after we take out those 2 enemies. And we can see here now we are at Church. So now we return true all the way back to village. So of course, what happens, we return true all the way back to the beginning, and of course, using our predecessor array, we construct our paths in reverse. Remember, we push back, and then we, of course, output it from the top to bottom. Of course, you can use a vector instead of a stack, because a vector you can do a pushback, and of course, then you can traverse the vector from size -1 to 0. So a little bit simpler. Now, for predecessor, every time you call a function on a neighbor, you update the predecessor at that moment. So every time you call function, you just keep updating that predecessor. So initially, you had village, you actually had, for Grand Hall, castle was the predecessor of Grand Hall originally. But when you called Grand Hall recursively from village, you updated Grand Hall's predecessor to be village. So every time you call a function recursively on a neighbor, at that moment you update the predecessor and then call the function. So anyway, that's the main algorithm. So hopefully this will help you. I don't think it's a very hard program, but again, for our final assignment, we have study week coming up. I don't want to make our final graph to be too insane. So it is just a variation of DFS. So I don't think it's anything too bad. Let's go to the input, and then we can sort of end this video. Before I actually go over the just the final remarks and the output, here's the other, here's input 2. So here's a visualization of input 2. So you can, of course, it'll help you, sort of guide you if in case you are having some issues with the assignment. But these are just red path from the village. That's going to be the path that should lead to the church. And it's their third one. So it's a very simple path, but of course you have to make sure you don't have lake as a first neighbor of village. So of course, if you read the file from the input, you will actually not have that one first. So it will cause a backtrack to happen all over the place until finally you return back to village and you find, oh, there's your simple path actually right there. So okay, now let's go ahead and talk about the output for the program. So anyway, here's the specification. So of course, write your recursive function, a global variable, document your code, and of course, don't modify the order of your neighbors list. So I just want to make sure it's in writing, so that way you can't say that I didn't cover that. Now this program, of course, you can just have one file, just your main file, and include all of your STL as needed. So anyway, for a sample run, of course, Ashley yells out Leon. You enter the map file, enemies file, I'm coming Ashley, and of course you output the path that leads to the church. And of course, second one, there's the other path, and of course the third input file, here's your third path, like that. So anyway, these will be actually used for testing on code grade. So I guess that's it for the video. So hopefully the video did help you, and I guess happy coding, and till next time.